Hi everyone. So in this bonus video, I want to go through a little bit more of the details behind the finite square well. So let's just pick up where we left off in the main class. So just to remind us, right, this is our potential energy graphed as a function of position here. We have the well with the height of the well is V naught, and the width of the well is A. We talked about, we can think of this as three different regions. One, two is inside the well, and then three is outside. We talked about the form of the wave function in all three of these regions. And I'm going to start from where we had used the boundary condition at infinity, namely that the wave function needs to nicely go to zero at infinity rather than blowing up to simplify us down to these forms. So we have this exponential c e to the kappa x here in region 1, d e to the minus kappa x in region 3, and then the sum of complex exponentials here in region 2. Just to remind everybody about the stuff we defined, we defined k in terms of root 2 me over h bar. Kappa is similar, depends on also v naught. And just to give us some context, right, our basic goal here is to be able to find the energy eigenvalues, namely E, and then the eigenfunctions associated with that energy. So when we left off in class, we were in the following situation, right? We're left with 5 total unknowns, A, B, C, D, and so the 4 constants here, as well as the energy E itself. Now, there are 4 different things we have yet to apply. So here are the boundary conditions we haven't used. We have not yet applied the continuity of the wave function at plus or minus a over 2. We also haven't applied the continuity of the derivative of the wave function at the same points. So that's sort of 4 different things, and we still have 5 unknowns, but that's okay, because ultimately we can determine an overall scaling constant for the whole wave function by requiring the wave function to be normalized. So we're good. At this point, we just have to crank through applying the boundary conditions. There's a little bit of sort of semi-magical algebra, but then we'll see where the result goes, and I'll show you how to read some of the figures in Townsend that graphically lead you to the energy eigenvalues. All right, so let's get started. So part A, let's apply the boundary conditions. So why don't we start off with the continuity of the wave function at x equals a over 2. So as I said in class, right, I think I worked this one out. So we just need to stitch together this form and this form at x equals a over 2. So that gives me a e to the I k a over 2 plus b e to the minus I k a over 2 equals d e to the minus kappa a over 2. Okay. Because we're going to need to refer to these equations subsequently, I'm going to just number this one. So I'm going to number this as, that's equation 1. Similarly, we can do continuity of the wave function at minus a over 2. Now we just have to look at this form and that form. Similarly, this gives us a e to the minus ika over 2 plus b. This time when I plug x equals minus a over 2 here, The minuses cancel in the exponent, so I have b e to the I ka over 2. And that all equals c e to the minus kappa a over 2. Again, this will be useful to have a number to refer it to, so I'll call that equation 2. All right, at this point, we're going to need to use the continuity of the derivative. So why don't I go ahead and differentiate psi 1 and psi 3. Maybe I can have rearrange this a little bit. Okay. So let's work out the derivatives first, and then we'll we'll be able to proceed. So d psi 1 dx, right? I differentiate this, I pulls down a factor of kappa, so I get a kappa c e to the kappa x. For region 2, I have like complex exponentials, so I have d psi 2 dx. Differentiating this term brings down an ik, so I have an ik a e to the ikx. I pull down a minus ik here, so I have minus ik b e to the minus ikx. And let me just factor this a wee bit. I'll factor the ik's out. So that gives me ik quantity a e to the ikx minus b e to the minus ikx. And finally, psi 3 here is quite similar to psi 1. So d psi 3 dx, so here I now bring down a factor of minus kappa from the chain rule, so I get minus kappa d e to the minus kappa x. Okay. So now, right, we want to, so condition C, continuity of my derivative, d psi dx, at, let's do a over 2 first. All right. So that means, so a over 2, I need to look at, whoops, can't see that. A over 2, I need to look at regions 2 and 3. Rearrange this, I think we're done here. Right, so I'm looking at regions 2 and 3. So let's plug in a over 2 here. And that gives me ik quantity a e to the ika over 2 and minus b e to the minus ika over 2 equaling on here in region 3 minus kappa d e to the minus kappa a over 2. Let's call this equation 3. And the last one we need to do right is continuity of my derivative at minus a over 2. So that's here, I'll call that d, continuity of d psi dx at x with minus a over 2. And now that gives, so here I need to stitch up regions 1 and region 2. So that, start with region 2 again. So that gives me ik, I plug in minus a over 2 here. So a e to the minus ik a over 2 minus b e to the, so minus a over 2 times minus I gives me a plus I ka over 2. Whoops. And that equals kappa c e to the minus kappa a over 2. All right, so that's all the boundary conditions. So let me box this, call this equation 4. Now we just need to keep on cranking at this and right, we still have a whole bunch of unknowns. So let me just pull our four equations together. So see if I can. So our next step, let's just sort of so B. So let's call this simplify. Right, we want to reduce the number of unknowns we have. So let's see. Right, so we have here. Okay, yeah. If I do this, you can see the results, I think. Right, so okay, so you can see all four uh, of these numbered equations, right? Notice that they all have they have a pretty similar form, right? 1 and 3 both kind of have A, B, and D in them. And similarly, 2 and 4 both have A, B, and C. It turns out this is a sort of a quantum mechanics algebra trick. We could actually get rid of the D's, right, by dividing these equations. So if, for instance, I were to divide equation 3 by equation 1, that would cancel my factors of D. And I could do the same thing with 2 and 4 to knock out my C's. That is, in fact, what we want to do here. So let's write this down. So eliminate D by dividing 3 by 1. That doesn't really matter which order I do it in because I'll keep my eyes in the numerator, so that's why I'll do 3 divided by 1. So doing that, right? So if I just divide both sides, right, then this gives me. Let's see what I can fit here. Let's see if I can maybe do this. Okay. I think you can just barely see one. So, okay, so for the left-hand side, right, we have ik a e to the ik a over 2 minus b e to the minus ik a over 2. The left-hand side of 3. Left-hand side of 1 is a e to the ika over 2 plus b e to the minus ika over 2. Whoops, and you can't quite see that. Okay, now you can see that. Okay, and then similarly for the right-hand sides, right-hand side of 3 is minus kappa d e to the minus kappa a over 2, and the right-hand side of 1 here is d e to the minus kappa a over 2. So I'm going to just set this aside. So notice now, right, the d's cancel, and in fact, all of this cancels. So I'll just send all of that away, and we're left with minus kappa on the right, equaling all of this on the left. So let me not bother to rewrite that. I'll just say that that equals minus kappa. All right, and this is a result. Let me call this equation 5 here. Okay. Okay, so similarly, and I'm going to need a new page. So similarly, eliminate C by dividing equation 4 by equation 2. And again, I think I'll have to just ask you to Believe me, I can't get all of this on here at once. But let's see. So new left-hand side of equation 4 is ik a e to the minus ika over 2 minus b e to the ika over 2. Left-hand side of equation 2 is here, and that gives me an a e to the minus ika over 2 plus b e to the ika over 2. And this now gives me, so right-hand side of 4 is kappa c e to the minus kappa a over 2. Right-hand side of 2 is c e to the minus kappa a over 2. Once again, oops, you can't see it. There we go. And once again, notice that like all of this cancels, and we're left with this whole nasty thing here equaling kappa. And let me call this equation 5. Okay, so this, in some sense, is better. Let me bring this page back. Okay, so you can see this. Okay, so in some sense, we're making things better. We've reduced sort of 4 equations and 4 unknowns. Oh, and 5 unknowns really. To now we just have 2 equations. And remember that our unknowns are still a and b, as well as the energy, which is sort of buried into, remember that both k and kappa depend on the energy E. So at this point, it's going to be a lot easier if I invoke a physics idea. Townsend, what he does is oh, I'm sorry, I was going to call this equation 6, right? And now I have 2 different equation 5s, so that's equation 6, right? And yes, they are in fact not the same. So yeah, so I guess they should definitely be distinct. Now, the way Townsend proceeds is that he sort of combines both equation 5 and equation 6, and sort of cranks on more algebra to argue that you sort of have 2 cases, that either a equals b or a equals minus b. You could go and do that. That's sort of a brute force approach. There's a more elegant way to think about this, and I think you'll learn more about sort of the elegant approach in Physics 421. If you're really curious, come talk to me. The elegant argument involves thinking about the parity operator that I introduced in the homework set for this week. But let me just sort of state this sort of physics result without proof for the moment. So invoke, let's call this, I don't know, theorem. Is it a theorem? Yeah, let's call it a theorem. Theorem, right? So which is the following: if v of x has even symmetry, right? Then the energy eigenfunctions are either or odd. Okay. So let me just state this without proof for now. So it's a case of an even potential energy, which is exactly what we have here, right? It's exactly symmetric about 0. It might seem plausible to you that such a potential energy does admit even energy eigenfunctions. The odd case is admittedly a little harder to come to terms with, but it does happen to be true. So let's look at this for a second, right? So let's just focus on what's going on in the middle of the well in region 2. So remember, so to think about this, so remember, right, the following, that cosine theta we can write as e to the I theta plus e to the minus I theta over 2, and that sine theta goes like e to the I theta minus e to the minus I theta over 2I. And you can prove this from the writing e to the I theta as cosine theta plus I sine theta. Now, let's look at this for a second, right? So, and let's think about symmetry, right? So, several ways to ponder this, but so let's just think about the even case for a second. You know that cosine x is even, um, and notice, right, that if I have a equals b, I have like e to the ikx plus e to the minus ikx, which is nearly cosine, right? So my claim, which I'm being a little hand wavy about, claim so if if a equals b, psi is even, um, right? At least in the middle, and similarly, right? If I have a equal minus b, I now have I have like e to the ikx minus e to the minus ikx, which is really close to a sine. And so if a equals minus b, then psi is odd. And you could go and just we can you could go and just sort of plug in a equals b and a equals minus b, and convince yourself that you'll be left with either an even or an odd function. Uh, and so it turns out that invoking the fact that the energy eigenfunctions have to be even or odd, right? Means that we can sort of analyze two cases, right? So this leads to analyze two cases. So a equals b even and a equals minus b odd separately. Right, it's because of this theorem, right? Because this theorem tells us that the energy eigenfunctions have to have either even or odd symmetry. That's what it allows us to make this leap to saying that, well, either a equals b or a equals minus b. For I think you can convince yourself that if a and b like differed by a factor of like 2, you will never be able to get the wave function here to be symmetric, either even or odd. Okay, so let's press on. So let me just pen. So let's call D. So let's do the even case. Whoops. First, right? And we have some choices here. So I can work with either equation 5 or equation 6. Let me start by working with equation 5 from earlier. So this is A equals B. If A equals B, I'll just replace my B's with A's. And notice that I have both A and B here, so I'll just factor that out. So that reduces to, let's see if I tutor this up, IK. I'll just factor out the common factor of A from both terms now. E to the IKA over 2 minus e to the minus IKA over 2 upstairs, and then downstairs I have A times the quantity e to the IKA over 2 plus e to the minus IKA over 2. This all equals minus kappa. Oh, and let me just say from equation 5. Now, it turns out that you'll get exactly the same thing if you use equation 6 instead, so it doesn't matter which one you pick. You do need both 5 and 6 in order to sort of prove that A equals B is a possibility, and Townsend does do that, but I'm going to take this shortcut here. So it turns out 6 gives same thing, right? And so, oh, and I need another page. This is getting, no, I think I can do the bottom here, so, right? So this is now a handy opportunity to use these two theorems, right? Because I have e to the I something minus e to the, oh, and that should be, sorry, that should be a minus IKA over, yes, that is in fact a minus IKA over 2, right? So this is an opportunity for that should be sine theta equals, yep. And so this is an opportunity for me to use that result, right? Because I have e to the I theta minus e to the minus I theta here. So I can rewrite my numerator as IKA times, to get just the numerator here, I need a factor of 2i sine, and my theta now is Ka over 2. Similarly, downstairs, I'll cancel my a's in the next step. I have e to the I theta plus e to the minus I theta, so that's 2 cosine Ka over 2 equals minus kappa. And let's keep cranking on this. And so this, okay, let's see. So so my a's cancel, right? So that's gone. And then this gives me, so I times I is minus 1. And oh, my 2's also cancel. So I get here minus k. I notice that I have sine ka over 2 divided by cosine k over 2. So that's actually minus k tangent ka over 2 equals minus kappa. Or if I just simplify this a little bit, I get tan ka over 2 equals kappa over k. All right, so this is getting us somewhere now, right? We've eliminated the A's and the B's. The only stuff we have left, right, is stuff that depends on E, right? Because both K and kappa depend on the energy. And so we've now sort of reduced this to one equation in sort of truly one unknown. The energy, albeit buried in a messy way within K and kappa. Let's continue with analyzing the odd case, and then we'll see where that shakes out. So the odd case, right, is A equals minus B. I'll use equation 5 again. Right, and this time, if I take my equation 5, so I'll flip the signs, so I get ik a, I'll pull out my a, I get e to the ika over 2 plus e to the minus ika over 2. Whoops. I'm setting b equals minus a. And then downstairs I have a e to the ika over 2 minus e to the minus ika over 2 equals minus kappa. Okay. Once again, I can simplify this with the help of my cosine and sine relationships here. If I do that, so upstairs looks like a cosine, so I get, so if I cancel first my a's, I get ik times 2 cosine, 2 cosine ka over 2. And downstairs I have 2I times sine ka over 2 equals minus kappa. And again, notice that, right, my factors of 2 cancel, my factors of I cancel, and then cosine over, oops, sorry, you can't see that, I hate this. Okay, right, you have cosine over sine, right, and now, right, cosine over sine is cotangent. I'll just choose to write it in this way. So this gives me, I'll divide both sides by k and put the minus sign over on the left for reasons that will become clear in a sec. So I get minus cotan ka over 2 equals kappa over k. All right, so this now gives me another equation like this one for my odd case. So where to go from here? So let's maybe number these equations. So let's call this equation 7 and equation 8. Okay, so now what's left? Solve 7 and 8 to determine my energies, E. Unfortunately, this is kind of a hot mess, right? Because both K and kappa have a rather complicated dependence on the energy. What we can do, though, to make our lives a little bit easier, notice that the trig functions depend on Ka over 2. We might want to use the strategy of lumping that all into a constant. So to help define, so see, let's define, Townsend uses the Greek letter xi, which is this like thing with a bunch of squiggles. So we define xi equals Ka over 2. And so now we have to remember that xi depends on energy, because K depends on energy. But notice that, right, K does have units of 1 over a length. So xi is dimensionless. Very often, it's helpful to try to like write or solve equations in terms of dimensionless variables. So let's write this as unitless. So our even equation, so this means that our even equation, which is 7, becomes tan of xi equals kappa over k, and then our odd equation, which is 8, becomes minus cotan of psi equals kappa over k. Well, it might seem that now in some sense we've made everything worse because we now have sort of yet another variable that depends on energy. But let's see if we can simplify it all, this ratio kappa over k that appears in both equations 7 and 8. So this is the part where we're going to feel a little bit sort of magical, but just bear with me, and then we'll go to the punchline. So let's see what we can get if we simplify kappa over k, right? So using their definitions, how far back are we? So we're back to here, right? I defined k and kappa when I was solving the Schrodinger equation. If I plug in those definitions, I end up with right some stuff that that simplifies a bit. So, oh yeah, but actually, sorry, before I do that, let me first at least make this a little bit nicer. I can just write this as kappa A over 2 divided by Ka over 2. Uh, and right, and so that at least gets rid of one of the, gets rid of K in favor of Xi. Because we ideally we have sort of all the energy dependence in Xi, and then if we solve for Xi, that solves for the energy. And then so now we still have to figure out what to do with kappa A over 2, right? But let's plug in for kappa, right? And so that if I pull the A over 2 out, right, that gives me, from the definition of kappa, which you can go and check, that gives me a square root of 2m v naught minus e over h bar divided by xi. Okay. Now, notice that this almost looks like xi. It looks like k, rather, except for this annoying factor of v naught. If we were to somehow to be able to pull a k out, we'd have ka over 2, and we'd have a xi downstairs. So maybe it might help if we can do that. Or the other thing we could do is I could just sort of pull this all. Actually, the simpler thing right now would be for me to bring this factor of a over 2 inside my square root. So let me do that. Yeah. So this means that I will have inside here. So let me just I'll need to square this, a squared over 4, and then I will pull, we'll have a 2m over h bar times v naught minus e, and this is all over, oh gosh, this is all over xi. Okay, so now that you can see that, so let's crank on this. So right, if I multiply this all in, right, this gives me 2 and an m and a v naught a squared over 4h bar, and then multiplying all of this by that, this gives me a minus 2m e over h bar times a squared over 4 and xi there in the denominator. Well, this is none other than k squared, right? And this is a over 2 quantity squared, right? This piece then, right, this piece is equal to k squared. And so all of this ends up equaling ka over 2 the quantity squared, which is none other than xi squared. Okay. So if I simplify that, I get a whole bunch of stuff. I can knock out the 2 there, so I get a m v naught. Oh, I made a mistake. Right, this h bar needs to be, it was outside the square root, so I need to square that there. And yes, now this is correct. Right, this is now correctly k squared, and that's all good. My bad. So yeah, so I can cancel my 2's here, and so I get an m v naught a squared over 2h bar squared this time minus xi squared over xi. Okay, we're almost there. But we notice that we've done something good now, right? Notice that we now have a bunch of stuff here that doesn't depend on the energy anymore, right? And so this rather depends on the setup of our potential well. It depends on V naught, the well height, and the width A of the well. So that's actually really good. This doesn't depend on the energy, right? So we've reduced ourselves to, right, this k kappa over k. We've reduced this to a function of xi only and constants. So let's actually just define this as a constant. So define constant. So I'll just sort of, for sort of symmetry, I'll choose to write this as something squared. Following Townsend's notation, I'll call this xi sub naught squared equals mv naught a squared over 2h bar squared, or xi naught equals by square root. This ends up being a over h bar m root m v naught over 2. So this now finally lets us rewrite our even and odd equations wherever I have them. I can now rewrite my even and odd equations. So I have, so for my evens, I have 10 psi equals root psi naught squared minus xi squared, okay, over psi. And for my odds, from my odd equation, here I have minus cotan. Psi equals the same thing, psi naught squared minus psi squared over psi. So these are now transcendental equations for psi. which, right, depends on the energy and gives us the energy, leading to E. And where all of this depending on the constant psi naught, which, as we said here, is related to the properties of our potential well. Transcendental means, right, we can't solve this algebraically, and that's where we get to the graphical method that Townsend uses. So I'm just going to go and grab that and try to put that under the docam. I'm going to have to probably adjust the focus, so bear with me. Okay, there we go. Okay. And this does not quite reach. Let's see if I can adjust that. Okay, let's see. Let me see if the focus. Okay, here. Focus is actually okay, I think. Okay, so that's what Townsend was plotting over here, like, in trying to solve the sort of even, sort of these even and odd equations. So we're plotting xi on the horizontal axis, and then, so this is the even equation here. So tan xi is plotted on, are these vertical branches, right? Tangent of psi is periodic. Now what's confusing is that each of these, like, downward lines is the right-hand side, namely root psi naught squared minus psi squared equals this, for one particular value of psi sub naught. So that's right. That's why this one's labeled psi naught small, and this one's psi naught large. So in practice, right, if you know, if you're given like some values for the well depth and the well width, you know what what psi naught is, or you can calculate it, and then that gives you sort of one particular one of these branches. Then the allowed energy eigenvalues are given by the values of psi, where sort of this curve for the right-hand side intersects tangent of psi. So let's sort of see what happens here, right? So if my psi naught is small, right, notice that, right, this just goes pretty quickly to 0 here, right? And then there's only one intersection with us. There's an intersection with just one branch of tan psi. But if we make psi naught a little bit bigger, right? And remember that psi naught, I can make psi naught bigger by either increasing the well depth or making the well wider. If I increase psi naught, right, now this curve picks up two different branches of tan psi. So what that means in practice is that there are now two solutions, or two bound state energy eigenvalues. We can keep on going with this. So for this larger one right now, there's I think we missed an intersection like up here, but now there are like 1, 2, 3, 4 intersections with branches of tan psi. So that gives us 4 allowed energy eigenvalues. We can do a similar thing here on this side, where once again we're plotting these curves for the right-hand side of our odd equation, and then these upward branches are minus cotan psi. And once again, qualitatively, the behavior's pretty similar. Okay. Notice that the larger psi naught gets, right? So the nearer each of these intersections happens to land to happening at like pi over 2, 3 pi over 2, etc. Uh, for um, uh, for the even ones here, or happening at like pi and 2 pi for the odd ones here. You can do that, and you can show that you recover the limit, the infinite square well as the limit of the finite square well in the limit as you take v naught to infinity, or which means, right, taking v naught to infinity means you're taking xi naught to infinity. So anyway, that's how you can read these graphs and how they sort of tell you about the allowed energy eigenvalues for the finite square well. So that was a lot of algebra. This was definitely not part of the scope of 218. But if you're curious about how it all shakes out, hopefully this helped to address that. Um, and so yeah, so at this point, you can, I think, focus on trying to understand physically what happens, and sort of probably the more illuminating thing, um, but sort of that backed up by all of this, is to look at some of the results in that PhET simulation. All right, see you next time.